Okay, our dear viewer, you are most welcome to the Tower Academic. My name is Lubega Juma Yasin. I'm a teacher of physics. So in our lesson today, we are going to talk about an electromagnet and how it is made. An electromagnet is simply a material which is magnetic that acquires that magnetism as a result of current flow. That's why we have electro. The word electromagnet comes from two words. One is electro, then the other one is a magnet. So electro comes from electric current. So under the influence of an electric current, we can have a magnet formed, and that is what we are going to dwell on in our lesson today. In 1820, Sir Ericsson Hans Ørsted came up with an experiment that shows that if a current flows through a conductor, there is a magnetic field which is set up along the conductor. So basing on that, the idea was harnessed to come up with the electromagnets, which have a wide range of applications today, as we are going to see. So I'm going to briefly describe or demonstrate how we can form an electromagnet. Here I have this, in physics we call it a solenoid. We call it a solenoid. You may wonder what a solenoid is. A solenoid is simply a cylindrical core which has an insulated copper wire that is coiled around it. As you can see, these are the coils around the cylindrical core. We call it a solenoid. Then I have this, I'm going to call it a magnetic material, which I'm going to magnetize, or which is going to form our magnet. Then on my right, I have pins. They are also magnetic in nature. Then the source of current, I'm going to use these electric cells. I'm going to use two cells. Now, before we can demonstrate, I want you to observe that if you have this material which is magnetic, if you bring it near the pins, you can see that nothing is happening right now. There is no magnetism acquired. So I want us to demonstrate, and you see that if a current flows through a conductor, it sets up a magnetic field, and it is that magnetic field that will magnetize this material. So briefly, these are called cell holders, and their use is to hold the cells together. Yeah, the cells are connected. So this is the solenoid. We have one terminal and the other terminal. So if you connect the terminals of the solenoid to the source of current, let's see what will happen. Yeah, usually when you connect the solenoid, it means that current starts to flow through the solenoid. Now, this is my magnetic material. You can see it does not attract the iron pins because it is not magnetized. Let us see what happens after some time when I press it inside a solenoid that is carrying an electric current. Okay. I think that is enough. You've seen before it was not able to attract the iron pins. Yeah, you can see. Because it is magnetic in nature, when we connect it to the source of current, that current flows through the solenoid, and we know that current flowing through a conductor sets up a magnetic field around the conductor. So it is that magnetic field that magnetizes the material. You can now see that we have formed a magnet. Usually the magnet formed is called an electromagnet because it is as a result of flow of electric current. Now what happens if you stop current to flow? It means the magnet will be no more because it is electro. It is controlled by flow of an electric current. Usually electromagnets are easily magnetized. When current is flowing, they form magnets, and if you stop current flow, they easily lose their magnetism. Let us have a look at what we have demonstrated diagrammatically. So basically, this is what we have. We have a cell connected to a solenoid in which a magnetic material is connected or is inserted. This is what we call the setup that brings us to an electromagnet. So when the switch K is closed, we shall have a current flowing through this solenoid, and we know that conventional current flows from the positive terminal to the negative terminal. So upon closing the switch, we shall have current flowing through this solenoid. Remember, a current flowing sets up a magnetic field. It is that magnetic field that will magnetize the material inside the solenoid. Now, we are talking about a magnet, and we know that a magnet has two poles. We have the north pole of the magnet and the south pole of the magnet. So after magnet being formed, we are not sure which pole is south and which pole is north. So to identify the polarity of the magnet formed, we use two rules. Number one, we want to identify polarity of the magnet. We are going to use two rules. Number one, we are going to look at how current flows in the solenoid, and that is called direction of current flow. When you look at current flowing in this solenoid, we have this left end, then we have the right end. So if you consider the direction of current, we are going to look at two poles because we have the north pole and the south pole. If I put arrows at the ends of letter N and put arrows at the ends of letter S, you can clearly see that if we are considering the current flowing, this N here, if you follow the arrows, you can see that this is anti-clockwise direction. Then on the other side, when you look at S, you see that current is flowing in clockwise direction. The solenoid, we see that current is flowing round and it is a cylindrical core. Let us apply it to our diagram and see. When you look at this end, my left end, you observe that current from the cell will pass on top of this solenoid where you can see, then it enters the other side. We cannot see this wire at the other side, but we can see this one at the front. The front wire is carrying current upwards, then the behind wire is carrying current downwards. So if you look at this side and observe how current flows, I'm going to use this marker to demonstrate. You see that current flows from this side, then it goes the other side, like this. If you look at this other left end, this is how current flows, like this, then like that. Now, if you bring this one and you turn the marker facing you, you see that this is the rotation or the direction of flow of current, and it is the anti-clockwise direction, because if you have a clock, it ticks in the other direction. This is called the anti-clockwise direction. So if current at this end is flowing in anti-clockwise direction, we move to say that this end of the solenoid is the north pole, because current flows in anti-clockwise direction according to this demonstration. Now let us look at the other end of the solenoid. If you stand at this end, you'll see that current, as it flows, here it is upwards, but the other end where you can't see is downwards. So looking at the end of the solenoid at the extreme right, you'll see that current flows like this, then behind, downwards. At this end, this is how current is flowing. So if I turn it to the observer, you'll see that this direction of flow of current is clockwise. Therefore, this end of the solenoid will give us the south pole of the electromagnet. That is looking at the direction of flow of current. Then we have a second one, which was suggested by a physicist called Fleming. It is called Fleming's right hand grip rule. Now, he suggested that you grip the solenoid in your right hand. When you grip the solenoid in your right hand, the current is shown by the fingers. Then the thumb will point in the north pole. So the thumb locates the north pole. If you grip this solenoid with your right hand, this is what I mean. Let me demonstrate. If you look at how current is flowing in this solenoid, you can see these wires on top. They are carrying current upward. So you hold or grip the solenoid looking at how current is flowing like this. It flows upwards, then behind it flows downwards. So you leave the thumb to point in one direction, and according to the rule, the fingers will point or they curl in the direction of the current. Then the north pole is shown by the thumb. So looking at how current is flowing, I've said it flows in upwards, where you can see, then behind it flows downwards. That's why I'm curling my fingers like this to show how current flows according to the diagram. Then this end where my thumb is pointing, that one is the north pole. So you can see that looking at the direction of current and looking at Fleming's right hand rule, they all bring us to the same answer. So this is the north pole and this is the south pole of our electromagnet, which is formed. So our dear viewer, do not forget to subscribe to the Tower Academic on our YouTube channel. Comment, like, and share such that we can learn from each other. When you look at the magnet formed, this magnet is not so strong. Looking at how we have arranged, this is a solenoid, but it has small turns. This is just for laboratory. But the magnets which are strong and are used in industries and so many applications, they employ more energetic and sophisticated materials. Now let's look. The strength of the magnet formed depends on factors like number one, the number of turns of the solenoid. So this is what we call a solenoid. The more the number of turns, the stronger the magnet which will be formed. And the fewer the number of turns, the weaker the magnet which will be formed. So depending on the strength required, the number of turns can be regulated to form the magnet which is of the required strength. Then we have another factor, which is magnitude of current. Magnitude of current. We said that this current here provides or produces a magnetic field. So the magnitude of current determines the strength of the magnetic field. Therefore, it determines the strength of the electromagnet which is formed. And the current is directly proportional to the strength of the magnetic field. And therefore, it will be proportional to the strength of the electromagnet formed, because it is this current which produces the magnetic field. In other words, the higher the current flowing through a conductor, the stronger the electromagnet which is formed. Then 3, we have the material which is used. We've seen that we have this magnetic material. We have magnetic materials like steel, like nickel, like iron. But for us to form a strong magnet, we use iron, because we all know that iron is easily magnetized and it acquires a strong magnetism. So if you want a strong magnet is produced if we use the iron as our magnetic material, because iron is strongly magnetized and it is easily magnetized. So that one brings us to the end of today's session. For more of this, please subscribe, like, share, and we make it so interesting. My name is Rebecca.